welcome back to the lecture series on bioelectricity. So, we have finished most of the animal bioelectricity. So, today we will be having the last lecture on animal bioelectricity. So, this is lecture number 29, and in this lecture we will be talking about the interfacing of the neuron with solid state electronic devices. So, as of now, if you go through the whole animal bioelectricity, we started with the basic architecture of the nervous system. Then we talked about the ion channels, we talked about the anatomy of the neurons and the transmission of signal from one neuron to another. We talked about the neuromuscular junctions, and we also talked about the cardiac system, which is also the other excitable membrane of our body. And in that whole process, you must have observed that we have used different methods of recording, using sharp electrode, using patch clamp electrode, using microelectrode arrays and few other techniques. But all these techniques could be coupled under one heading. These were all the techniques where electrochemistry was involved. So, there is an electrode in direct contact with the cell, and there is a electrolyte where that cell is growing, and whatsoever changes are there is sensed by the electrode out there. So, these kind of recordings are mostly invasive recordings, barring aside the recording made from the microelectrode arrays. Most of it is an invasive recordings. So, there always remained an effort to have a non-invasive recording. One of the example what I showed you was the microelectrode array, but the problem with microelectrode arrays or any kind of electrochemical methods of recording is that the signal is lost very significantly. So, whatsoever signal we are receiving in that whole process is kind of compromised big time. So, there remain a continuous efforts on the part of people who are interested in interfacing neurons with the electronic system, that we should have better and better techniques in order to record from the neurons, because the better recordings we have, the more signal we will be able to derive from the neuronal activities. So, in that same line, today's lecture, the 29th lecture, is about the interfacing of the neuron on a solid state electronic devices. So, in this situation, what we will be discussing for next 30 to 40 minutes is how you can interface a neuron on an electronic circuit and any neuronal activity which is sensed by the semiconductor devices. As of now, we only talked about the simple electrodes. Either you use a patch electrode, or you use a sharp electrode, or you use a glass electrode, or you use a extracellular electrode. All these falls under. So, if I had to classify, I have to classify them under two headings. So, electrical. So, the broad class is electrical recordings from neurons, and neuronal network. Okay, from neurons, and I am just put NN neuronal network for you. Okay. So, these could be classified under two broad headings. One is the electrochemical methods, which we have discussed in the form of microelectrode arrays, MEAs. We talked about patch clamp, we talked about sharp electrodes. Okay. So, now we will be talking about a different class. This is the class we have already done. We will be talking about using semiconductors, where we are dealing with a different kind of charge transport. So, in this situation, if you see all the electrochemical charge transport, they all involve ions. It's all the charges what we are talking about. If I represent charge by q, all the charge transport is in the form of ion, and we are dealing with, one second, we are dealing with ionic fluxes. So, in the neuron, we see a ionic flux which is being detected by an electrode. This is what is happening. But in this situation, whenever we talk about a semiconductor device, we talk about electrons. So, whatsoever, so now the interfacing is like this. You have the neuron which is functioning as ion transport or ionic flux, and you have a detector which involves electron transport. So, you are marrying two different branch. One is the ionic transport, and you are detecting using an electronic devices. So, coming to the slide. So, this is the first slide, talk about the field effect transistors. In other words, the solid state electronic device to study neuronal activity or the electrical activities of the neurons. Okay. So, I am just giving a nice picture of the neuronal network in a close proximity, a single neuron with all its processes you could see, and underneath there is a picture of a field effect transistor at a very high resolution. Okay. So, what really we are trying to do? So, if you see the second slide, it is basically what we are trying to do is electrical interfacing of semiconductors and nerve cells. So, direct electrical interfacing of semiconductor and nerve cell is the physical basis for a systematic development of hybrid neuroelectronic system. So, neuro part is out here, this is your neuro part, and this is your electronic part. Okay. So, that is what we talked about, hybrid system, because these are two different systems which are making a hybrid neuroelectric devices, and which someday, somewhere in a distant future possibly, will have neuronal computers, neuroprosthesis governed by the interfacing of semiconductor devices with our own nervous system. This is basically we are exploring the new world at the interface of the electronics in inorganic solids and ionics in the living cells. That is what I was trying to explain. This is the ionic world we are talking about, and semiconductor is the electronic world we are talking about. So, coming back to the slide, if you see, the basic research provides the basis for future application in medical prosthesis, biosensorics or biosensors, brain research, and neuronal computation, which someday the kind of algorithms which are followed by the neurons in their computational ability, which you must have observed while we were discussing of learning, memory, could be utilized for developing better electronic system, memory storage devices, so on and so forth. Okay. So, this is, that is why I wanted to close down this segment of animal electricity with this interfacing part, where a lot of research is going on all over the world. Okay. The relevant literature, I have cited this last paper, if you see, from Peter Fromherz and Andreas Oppenhauser, J. Weiss and T. Vetter. So, this is one of the seminal paper which was published in the journal Science back in 1991, a neuron silicon junction, a reduced cells of the leach on an insulated gate field effect transistors. It was probably one of the very, very seminal discovery. And please go through the work of Peter Fromherz, he is emeritus professor now in the Biochemistry Institute of Max Planck Institute, Biochemistry Institute. So, go through some of his work, because he is one of the pioneer. He worked along with several people, Andreas Oppenhauser and all these other people, and he was involved in kind of giving birth to this extraordinarily challenging area of interfacing neuronal system with the semiconductor devices, and which involves a lot of technical expertise, a lot of understanding of device physics, because you have to realize that when you are dealing with a semiconductor, you really have to understand the device physics very right. And then on top of this, you have to, in the one of the last slides, I will show you how those chips were being made. They are keep on improving, but at this stage I will show you one of the primitive chips which were developed by Peter from Hertz. So, and most importantly, a dare to dream, 1991. It's long time back almost now. I mean, it's almost more than 20 years. Dare to dream for something which was not seen before. So, I will request you please go through this paper, and I will add few other materials, some of the patents which has been filed by Peter from Hertz and Max Planck. Go through this paper, which was published very more recently, that 2005. And there are several papers, but these are the kind of papers which may interest those who are interested on understanding what we really mean by neuron silicon transistors. So, here in this section, I will only touch the very basic fundamentals. I am not going to get into the device physics, because that is beyond the scope of this course, because that may consume another 15 or 20 lectures all by itself. Okay. So, I will just, because I am devoting only one lecture, to give you an overview, that so that you can build upon the story on this. So, you do not expect that I am going to go to all the details of the devices, but I will give you the key points which will help you to develop the story for your further endeavor. Okay. With this relevant literature, I will move on to what we are trying to do. So, basically now this it is clear, it is a neuron silicon interface we are talking about, a powerful tool for brain research, information technology, because that is where possibly, because if you look at it, now coming back, if you look at the current state of art with information technology, we are reducing the size of the transistors, or the computational hardware day by day, but there is a limit. We cannot go beyond it. But look at your own brain, that small structure is making all the possible computations. If we really even understand 20%, if we could really mimic in the electronic industry of what the real neuronal network in the human brain is functioning, we could make a quantum jump from the current state of affairs with all the silicon based electronic system. And just to give you a small detour from here, whenever I am talking about silicon based systems, so if you look at the semiconductor, because this one of the lectures I will be giving at the fag end, while I will be talking about some of these amorphous silicons. And so, if you look at the semiconductor industry, semiconductor, most of us always associate it with during 1940s and 50s with Budd in Britain and Shockley working on crystalline silicon and made the discovery. But it is interesting to note that semiconductor behavior was observed much earlier than that. It was initially observed by Michael Faraday while working with some of the sulfide molecules, but he really could not explain this nonlinear behavior. Followed by that, it is some of the works by Sir J.C. Bose with Galena and few other people at that point of time. They discovered this semiconductor effect at that time, back in 1800. But the real success story in terms of commercializing it and really formalizing as an independent discipline started since 1940. That is why here we will be talking about the neuron silicon interface, but just to remove a doubt, this could be something else also, any other semiconductors. So, whenever we talk about, just give me a second, let me just, okay. So, this whole thing, as far as your imaginations can go, so what you see here is something like this, okay, on your slide, neuron silicon interface. So, this might as well could be written neuron semiconductor interface instead of silicon. Okay? And this will include everything, you will have crystalline silicon, you have amorphous silicon, then you have cadmium sulfide, then you have FeS2, all the different sulfides and everything, then you have organic semiconductors and everything. So, this part can go up and up and up and up. Okay. So, any of these materials which could be used to detect the neuronal signal should fall under this broad heading of neuron silicon interface, okay, or neuron semiconductor interface. Fine. Now, coming back to the slides. So, what is the difference between, let us start with some of the basics. What is the difference between a brain and a computer? So, one of the fundamental difference, computer and brain both works electrically, that we know. So, both of them have electrical impulses, but the problem is silicon based computers utilize electrons as their charge carriers. On the other hand, neurons utilize the ions, sodium ions, potassium ions, magnesium ions, calcium ions, like so on and so forth. Okay? Fluid as the major charge carriers. Now, if you see the speed, that is stunning on the slide. Electrons in silicon have a mobility of 10 to the power 3 meters square, okay? Whereas, the mobility of the ions in water is far, far less. See the difference in the speed. Ionic fluxes are, as I was showing in the previous, while I was kind of putting it down on the board. Once, give me a second. Ionic fluxes are extremely speed wise, this speed is very, very high. So, you are interfacing two systems whose charge carrier mobility is totally different. Okay? The difference of mobility is the fundamental difference of these two information processors. So, you are marrying an ionic system with an electronic system. Now, here I just give you an example on the slide how it looks like. Now, we will divulge the story. Okay. Neuron growing on a field effect transistors. Now, what we will do, so you see in a field effect transistor there is a source, there is a drain, and in between you see this whole yellow thing. This is nothing but a neuron growing on a semiconductor device. Now, we will talk about in the coming slides what is a field effect transistor and what is that at the interface, what are we really detecting. Okay. So, now starts our journey of interfacing neuron on semiconductor devices. Okay. Ionic and electronic interface, we have a little bit talked about it here. Just recap, the previous figure shows a neuron silicon chip, the figure just now I showed you this figure. So, it is basically showing an individual nerve cell from the rat brain and a linear array of transistors. Okay. This nerve cells, which is 20 micron in a diameter, is surrounded by membrane with an electrically insulating core of lipid, as you know that there is lipid bilayer or around the neuron. The lipid bilayer 5 micrometer in thickness separates the environment with about 150 millimolar sodium chloride, which is the extracellular solvent, from the intracellular electrolyte with about 150 millimolar of potassium chloride. We know all these things. Ionic currents through the membrane are mediated by specific protein molecules, which you know as the ion channels. These ion channels have a conductance of 10 picoseconds to 100 picoseconds. So, now this is the timeline, or this is the kind of current what we are trying to measure. Now comes what is the field effect transistors. So, let us try to understand what is a FET, which is in short it is called FET. The field effect transistor relies on, now this is where I have highlighted is most important for you guys to understand, on an electric field to control the shape and hence the conductivity of a channel of one type of charge carrier in a semiconductor material. This is the key point and the key word is your electric field. Okay. If there is a change in the electric field, it changes the signal. FETs are sometimes also called unipolar transistors in contrast to single carrier type operation. Okay. Just for your understanding here, let me tell you the discovery of FET is much before the discovery of crystalline silicon semiconductor devices. It is, as we will go to the history, you will observe that the discovery took place somewhere in 1930s and much before that. Actually, there are patents much before that. Okay. So, coming back to the FETs are sometimes called unipolar transistors. In contrast, they are single carrier type operation with dual carrier type operation of bipolar junctions, which is also called BJTs, okay? Bipolar junctional transistors. The concept of FET predates the BJT, though it was not physically implemented until after BJTs due to the limitations of semiconductor material. This was one of the challenge what FETs had, and the relative ease of manufacturing BJTs compared to FET at that time. And if you see the history, the principle of field effect transistors was first patented by Julius Edgar Lilienfeld in 1925 and by Oscar Hale in 1934, but practical semiconducting devices, okay, using the junctional field effect transistors, the gate field effect transistors were only developed much later after the transistor effect was observed by the team of William Shockley, Barden and Britton at Bell Lab in 1947. So, you see, I mean, there is a technology, but the technology really could not pick up because there are manufacturing problems, there are problems of getting pure crystalline silicon, because those are really tough thing, and followed by the MOSFET or the metal oxide semiconductor field effect transistors, see, which largely supersede the JFET and had more profound effect on electronic development, was first proposed by Don Kang in 1960. So, this is briefly the history of FET. Now, talking about, you saw something out there, there is a source and the drain and all those things. What are those? So, what really are the terminals of FET? So, those of you who have seen a simple transistors, you remember that simple transistor has, if you look at a second. So, if you see those old style transistors, you will see there are sometimes 4 leads coming out. So, this is the transistor here, and then these are the leads which are coming out. So, one is a collector, one is an emitter, one is a base. Okay. Similarly, the FETs also have different terminals, and today we will talk about the terminals in this slide. Okay. If you look at the slide, all FETs have a gate, they have a drain, and there is a source terminal that corresponds roughly to the base, collector and emitter of the BJTs. So, you see the base, collector, emitter, the correspondings are the gate, drain and the source. Okay. Aside from the JFETs, all FETs also have a fourth terminal called the body, base or bulk or substrate. These are all synonymous. Okay. There is a body on which, and as a matter of fact, you see the body where all these cells were sitting on top of the gate and all those things. Okay. This fourth terminal serves as the bias the transistor into operation. It is rare to make a non-trivial use of the body terminal in circuit designs, but its presence is important when setting up the physical layout of an integrated circuit. The size of the gate, length L in the diagram, is the distance between the source and the drain. The width is the extension of the transistor in the diagram perpendicular to the cross section. Typically, the width is much larger than the length of the gate. Okay. So, again, let me tell you, you really do not need to get to the physics of this device. You have to understand the basic concept, how you detect the neuronal signal. That is the most important thing which I wish to highlight. Coming to the next slide, the functioning of the FET. The name of the terminals refers to their function. The gate terminal may be thought of as controlling the opening and closing of a physical gate. This gate permits electron to flow through or blocks their passage. So, it's gate is basically, you open the gate, there is a flow of electron, you close the gate, the electron flow is being halted. Okay. Now, coming back to the slide, this gate permits electrons to flow through or blocks their passage by creating or eliminating a channel between the source and the drain. Now, here is the key line which is important for you people to understand. Electrons flow from the source terminal towards the drain terminal if influenced by an applied voltage. So, the electron flow is regulated by an applied voltage or a field. The body simply refers to the bulk of the semiconductor in which the gate, source and drain lie, which is kind of casing almost. Usually, the body terminal is connected to the highest or lowest voltage within the circuit depending on the type. The body terminal and the source terminal are sometimes connected together, since the source is also sometimes connected to the highest or lowest voltage within the circuit. However, there are several uses of FETs which do not have such a configuration. So, do not get into that. What is most important is that if you look at between the source and the drain. So, if you see the electron flow from the source terminals towards the drain terminal. So, if you see this picture now from the source to the drain, you see in the picture there is a source and there is a drain, and in between on the gate there is an electron, there is a neuron which is sitting out there. So, the flow of the electron from the source and the drain is regulated by the applied voltage. That is what was being shown here. The electron flow from the source terminal towards the drain terminal is influenced by the applied voltage. Now, how we get this applied voltage? If you realize here, across this, if the neuron is sitting, that neuron is continuously cross talking. Now, let us see what is happening, because when it is this neuron is cross talking, there is a change in the field, there is a change in the voltage at that particular site. We will have a much better view as we will move through. Okay. Now, coming to the reason for silicon at the interface, this is just a little off and then I will again come back. Silicon is chosen to be electrically conductive substrate for three reasons. Okay. First, coated with a thin layer of thermally grown silicon dioxide. Silicon is a perfect inert substrate for culturing nerve cells. This is one of the reasons why we are using, because you need a substrate where the neurons can grow. You need a substrate which could be modified with different kind of proteins, so that it supports the growth of the neurons. Second, a thermally grown silicon dioxide suppresses the transfer of electron and the concomitant electrochemical process. So, this essentially means is that there should, so if you see this picture, when you are growing something like this, you have to ensure that there is no leaching taking place, because you are on top of a semiconductor device. There is a lot of water, because whenever we talk about electronic devices, even think of this, they always say don't go to water, or you have your cell phone, all of you carry a cell phone, and likewise don't go to the water, they will go bad and all those things, because the water will percolate, there will be short circuit and anything could happen. So, now you are trying to have a dry electronics. So, whenever we talk about semiconductor, we talk about a very dry system. You have to keep this system away from water, whereas whenever we talk about ionic motion, we are talking about the wet electricity. If this is the dry electricity, then this is the wet electricity. Now, you are trying to interface a dry electricity on a wet electricity, because all the neuronal activities are all wet electricity. So, you need to choose a substrate which could suppress the transfer of electron and the concomitant electrochemical processes that leads to a corrosion of silicon and a damage to the cells. So, you have to realize this is a very tricky thing. As a matter of fact, for any kind of device you make, you have to ensure that the device is not corroding out there because of the continuous presence of electrolyte on top of it. Because here is an electronic device, semiconductor on top of it, I have this fluid continuously moving through, and there are cells which are secreting all kind of proteins and what not. So, you have to ensure that there is no corrosion, there is no leaching, there is no toxic, because underneath you have silicon, you could have any kind of semiconductor material what I was showing you. So, you have to ensure that they are not getting corroded. Okay. And the last, a well established semiconductor technology allows the fabrication. This is partly because the electronics industry since 1960s has taken quantum jumps in terms of manufacturing. So, there is a ease of manufacturing. You really do not, there are very well set clean rooms. You can, depending on the level of purity you want, you really can place the semiconductors, and you can place the transistors at a specific geometry. You can do a whole series of you could vary the size of the gate, you can vary the size of the whole device, and there are series of manipulations which you could do. So, that is why people preferred the silicon based system. So, coming back, what is happening? So, now if you look at this picture, this is a very interesting picture. So, I showed you, now you see the underneath what is there. So, you have this neuron which is in yellow, underneath you see there is a source and there is a drain, then there is a gate which regulates the flow of electron from the source to the drain. Okay. Now, you see those two arrows from left and right, these are the currents, which are basically the ionic fluxes which are moving in and across the cell. So, whenever there is ionic fluxes moving, so what is happening? So, if you try to imagine, if you see this picture, it will make more sense. Now, so here you have the cell sitting. I am just redrawing what is there in your slide, and here you have the electronic device, and here you see this yellow arrow coming through. Now, if you refer to the slide again, you will see that. Okay? These yellow arrows are nothing but the influx, or and in this zone there is a change in voltage and change in, just showing the change in field, or change in electric field, I should put it, change in electric field. Now, coming back, our field effect transistors, now read that on your left hand side. The field effect transistors FET relies on an electric field to control the shape and hence the conductivity of a channel of one type of charge carrier in a semiconductor material. Now, you see how the gate voltage could change, because depending on that opening and closing of the gate, it will decide how much current from the source to the drain will flow. Okay? So, this is the fundamental basic what you need to understand, and try to understand these things diagrammatically instead of getting into all the technical things, because you have to understand, visualize the whole process. If you visualize the whole process, then you should go to the technical part of it. Without understanding the having the basics clear, do not jump into the technical jargons, you will get lost completely into this. Okay? So, now neuronal recordings from field effect transistors. So, the caption, what is the picture, what you saw is basically there is a rat neuron on electrolyte oxide silicon field effect transistor. The electron micrograph of hippocampal neuron, we have talked about it in the silicon chip with a linear array of p-type buried channel transistors after 8 days in culture. So, this was the 8 days the cells are growing. Now, you realize why it is important to ensure that there is no leaching taking place, because 8 days, 20 days you are growing a neuron on top of a silicon chip. If there is a leaching, this cell will die. Okay? Now, coming back, the surface of the chip is chemically and structurally homogeneous, consisting of silica with a surface profile below 20 nanometer. The schematic cross section of a neuron on a buried channel field effect transistor with blow up drawn to scale of the contact area. During an action potential, current flows through the adhering cell membrane and along the resistance of the cleft between chip and cell. The resulting extracellular voltage in the cleft, this is the most important line. The resulting extracellular voltage in the cleft modulate the source and the drain current. So, this is exactly what I was trying to tell. This change here, this change is this what this source and the drain is sensing. So, there is a gate out here. That is it, and that is the most fundamental thing. That is why I am repeatedly telling you, try to visualize, take a sheet of paper, draw it and try to visualize. Once this is clear, then you can read all these papers and slowly develop the technical know-how about it. Okay? So, this last line, the resulting extracellular voltage in the cleft modulates the source and drain current, and this is where lies the catch. Now, if you look at the recording setup, this is how the recording setup, and by the way, these are all taken from Peter Fromhert's patents and works which are published online. Okay? So, electron flows from the source and drain terminal if influenced by an applied voltage. Applied voltage, the influence is coming from this neuron, or it could be anything, it could be a cardiac cell, but it has to be an excitable cell which continuously changing its voltage, extracellular voltage. Okay? The electrolyte filled cleft between an isolating object and an electrode forms the sealing resistance. By measuring the Nyquist noise of this resistance, one can determine the properties of the sealing, such as its extension, the cleft width and its change over time. So, this is exactly how these measurements are being made. Now, let us see what happens when the silicon. So, what is the process systematically? Let us go through it. Okay? When nerve cells grow on a chip, they deposit cell adhesion protein, they secrete proteins. to provide cell anchorage. So, these cells adhere to the surface. These proteins keep the lipid core of the membrane at a certain distance from the substrate. You look at it, they are at a certain distance. They are at a certain distance. Look at this. They are at a certain distance where you see this current. So, there is a certain distance which is being maintained. Okay. These proteins keep the lipid core at a certain distance from the substrate, stabilizing the cleft between the cell and the chip that is filled with electrolyte. The conductive cleft shields the electrical field and suppresses a direct mutual polarization of silicon dioxide and membrane. The cell silicon junction forms a planar electrical core coat conductor. The coats of silicon dioxide and membrane insulate the core of the conductive cleft from the conducting environment of silicon and the cytoplasm. Step 2, the activity of the neuron leads to ionic and displacement current through the membrane. The concomitant current along the core gives rise to something which is called transductive extracellular potential. So, this is what that change is. This change in voltage is what is transductive extracellular TEP. What you see in your slide now, that is what we talked about, transductive extracellular potential. Meanwhile, a voltage transient applied to silicon leads to a displacement current through the oxide core. Thus, the TP appears between the chip and cells due to concomitant current along the cleft. In the second stage of interphasing, the TP in the core coat conductor is detected by voltage sensitive devices in the chip or in the cell. You could have voltage sensitive dyes here, which could detect the change. You could have a voltage sensitive dye here, voltage sensor here, which could see the change of the TP. Okay. Now, what happens when the nerve cells? This is the last part. The interphasing of the neuron and semiconductor is mediated by transductive extracellular potential. A large TP results from high current through membrane and silicon dioxide and from a low conductance of a junction. Recording and stimulation of neuronal activity are promoted by a small distance d, high specific resistance P, and a large radius A of the cell chip junction. Efficient recording requires high ion conductances G in the attached membrane, efficient stimulation, high specific capacitance C of the chip. Okay. Now, coming to the actual recordings, this is how the actual recordings look like. So, here again you see the neuron sitting out there. This is in black and white, you just have to, and all those 1, 2, 3, 4, 5, 6 up to 8 you see, those are the gates. Okay. Those are where the source and the drain, source and the drain, source and the drain likewise. So, if you look at it at different source and drain, so from one single neuron, now think of it, while we were talking about the, say for example, I talk about this cell, okay, and I want to record from it. I could put 1 electrode, 2 electrode, maximum 3 electrode, but every time there will be a lot of leakage and there will be a lot of loss of ions. I cannot really do that. And in the case of patch electrode, you will have this big a patch electrode. I cannot. I mean, it's really tricky to put. Maximum you can put 4 patch electrode. If you are really, really good, you have to be absolutely amazing to do that. Okay, but look here, from one cell, just from a single cell out here, sitting out there, how many gates are there? At least there are 8. I can guarantee you this could be reduced down to 16 also. So, from one single neuron at one point of time, you are recording from here, recording from here, recording from here, recording from here, from all the possible zones you can make the recordings. This is the power of this technique. With electronics, which is far more smaller than the ionic, all these electrodes, okay, you can make multiple recordings. So, this is the profoundness of this technique. Why this technique is being followed so extensively is this. You really can make a significant amount of recordings, and if you see it, see in the 1 you do not see a change, 2 you do not see a change, 3 do not you see, 3 you started seeing the change if you look at it, and the 3rd you will see a change, 4th gate you see a change, on the 5th gate you see a beautiful change, 6th gate again I mean not discernible, I mean it's kind of there, 7, 8 you hardly see anything. So, the noise on the extracellular voltage due to the cell radiation, and this is very important, the extracellular voltage recorded by the transistor within a bandwidth of 1 hertz to 10 kilohertz. The transistor beneath the cell body exhibit an enhanced noise near the end of the traces. The transistor number 3 and 4 and 5 recorded spontaneous neuronal excitation. 3, 4, 5, there is a spontaneous neuronal activation, which is very tough to pick up. These signals are very, very tough to pick up with an extracellular electrode or any other kind of electrochemical devices, which you really cannot do. And if you see, this is how the transient goes when the FET signal during the depolarization followed by the relaxation. This is what we call as cell transistor hybrids. So, if you look, I was telling you that in one of the last slides I will show you, this is how the chip look like, encapsulated chip. If you look at that encapsulated chip underneath, so there is a glass on the top, there is almost a glass, should say, teeny tiny glass plate, with the wall surrounding it. So, you plate the cells on top of this encapsulated chip. This is the left hand bottom figure what you are looking at. Okay. On top of this, in that small dish, you culture the cells, and those cells, underneath those cells are the embedded are the electrodes. So, those neuronal activity what is taking place inside that chip are being sensed by the chip or by the gates which are underneath it. And this is the in-depth detail of the different gates. You see those gates out here with in the top left figure, in the green and yellow, you see the gates you will see with the orange and the yellows will give you where the source and the drains are, and this is the individual gate. So, this is where we are. The modern semiconductor technology could provide suitable tool for massive parallel monitoring of neuronal activity at high spatial and temporal resolution. Because why it is in high temporal and spatial resolution? Because you could get recordings from both spatially as well as temporally over a period of time. You see, say for example, let us see an hypothetical situation. Say for example, in a neuronal network, if you could grow a wonderful network on top of an FET, say this is the neuronal cell body which is involved, and you have a gate here, you have a gate here, you have a gate here, you have a gate here. All these are different zones where the gates are. Okay. Now, over a period, if the signal is moving like this, over temporally you can measure the signal, temporal measurements, as well as you can measure at different place in the space of it. You can get it from the dendritic arbor, you can get it from the axon, you can get it from the cell body, you can get all the way to the down of the axonal terminal, likewise, and so on and so forth. So, you see all the signals what we obtain from FET is far more powerful than using an extracellular electrode, and it is a very non-invasive process. This is a technology which is slowly developing. It will take time. It is not easy to interface. There is a lot of research which is needed in biomaterials, to interface this semiconductor materials, but this is where the future lies, and that is why I pulled this up as the last 29th lecture of the animal bioelectricity. This is what people are trying to do, interfacing semiconductors with neuronal system. So, I will close in my lecture here. So, I believe I request you people, please go through the Peter Fromhert's work, Andreas Oppenhauser's work, and a few other works. Some of the Italian groups are working on organic semiconductors to interface cells using pentacene and all these kind of molecules. Please go through this. Okay? Thanks a lot.